Greetings and salutations, magical chemists. Are you ready to learn about catalysts in all of their glory? A catalyst officially can be defined as something that increases the rate of a reaction without being consumed in the reaction. There are all sorts of different catalysts. Some provide a surface with a better orientation or an alternate pathway for the reaction. Basically, they increase the number of effective collisions. Most of the time, this means that they're going to replace a single high activation energy step with two or more lower activation energy steps. So you will actually need to draw a new potential energy diagram for the catalyzed reaction. A catalyst works in a reaction mechanism. You'll see it being consumed. It exists at the beginning and it gets used up in an earlier step, but then it's reproduced in a later step. It is important to note that a catalyst does not change the thermodynamics of a reaction, only its kinetics. Basically, it's going to speed up the reaction, but the delta H, the enthalpy change, is going to be the same. So let's look at an example. So here you have ozone gas reacting with an oxygen gas atom to produce two oxygen gas particles. Well, this is super slow. It's got a really high activation energy. But if you add a catalyst, so the catalyst in this case will be a single chlorine gas atom. So then now we have a two-step mechanism. So notice when we have the catalyzed reaction, we have a two-step mechanism and each one of those steps is going to have their own activation energy. But notice how both of them are lower than the activation energy of that original uncatalyzed reaction. Now, it's important to distinguish between a catalyst and an intermediate because both of them are species that appear in a reaction mechanism but not in the overall reaction. So when you add up the steps of your mechanism, catalysts and intermediates are going to be crossed off, but they are different things. So the trick is, if a species forms as a product in an earlier step and is used as a reactant in a later step, that would make it an intermediate. However, if the species is used as a reactant in an earlier step, but then is reformed as a product in a later step and it cancels out, that makes it a catalyst. So let's try an example. So here is a particular reaction mechanism. It's two steps. And I would like to know, does this reaction mechanism have an intermediate or does it have a catalyst? Or neither, or both? I just don't know. So I would like you to try to figure it out. And then when you are ready to check your answer, unpause the video. But pretty please make sure and try it first. So if you're looking for intermediates and catalysts, you're looking for things that will get crossed out when you add the steps together. So I minus, our iodide ion, is indeed one of those things. Hopefully you were able to identify that I minus is a catalyst because when you first see it in the early step, it is a reactant and then it is consumed in a later step, So when you first see it, it is a reactant being consumed and then it is produced in a later step. In this reaction mechanism, there is also an intermediate. So the hypoiodite ion, yum, polyatomics, is produced in the first step, but then it is used up in the second step. So again, it will be crossed out, but shows up first as a product and then later as a reactant. So that's why the hypoiodite ion is considered an intermediate. So there you go. So identifying intermediates and catalysts are very common, both multiple choice and free response questions. You have to be able to recognize them and explain how you can tell them apart. All right, let's take a look at the next page. Okay, so we're looking at a given reaction, and this is the uncatalyzed reaction right here, the one-step, very slow process that is occurring. What we want to see is how you would modify this reaction pathway to show what would happen if we catalyze the reaction in a way that would result in a two-step process. So you need to both be able to draw your new reaction pathway and you need to be able to explain it. So first, go ahead and pause the video, and I want you to do this part first. So draw it first, and then let's see if we can explain why it is the way it is. All right, let's see what you got. When you're ready to check your answer, unpause the video. All right, so if you were grading this on a free response problem, there'd be two parts to this answer you're looking at. The first part is that you have to have two distinct bumps, because of course there are two distinct steps. But the other part is that the height of the very first bump, the activation energy, if you want to be specific, has to be higher than the activation energy of the second step. But why? Well, remember, look at the mechanism. Where's the slow step? Well, the very first step is the slow step, and if that's the slow step, it must have the higher activation energy of the two steps. All right, so now we need to explain what the heck we just did. So take a moment and try your hand at using wordy words. They're delicious. And when you're ready to check your answer, unpause the video. Okay, so first we need to explain why there are two bumps. Well, there are two activation energies, one for each step in the mechanism. And both of those are going to have a lower activation energy than the uncatalyzed reaction. But we also need to specify the idea that the slow step will have a higher activation energy than the fast step. So that's why the first activation energy is higher than the second. And there you have it. An explanation along with a beautiful catalyzed reaction pathway. All right, let's take a look at the next one. The next one says modify the diagram to show any changes that result when the starting temperature of the reaction was doubled. Warming things up. And then you're going to explain your reasoning. So, reaction pathway, explanation. Go! When you are ready to check your answer, of course, unpause the video. Haha, did you catch my trick? It's a trick question. There is no change to the reaction pathway. Increasing the temperature does not affect the activation energy or the reaction pathway. All it does is increase the number of effective collisions. Okay, so we have one more to look at. Part C. This one says, okay, that's great. Modify to show the change in the reaction pathway would result when the concentration of ozone, which is one of our reactants, was decreased by a factor of 3, and of course, explain yourself. So, take a moment, draw delicious reaction pathways, and explain, and when you're ready to check, well, unpause the video. Are you getting wise to my tricks yet? There is still no change, because decreasing the concentration of reactants does not affect activation energy or the reaction pathway. It will decrease the number of effective collisions and thus lower the rate, but that doesn't change the potential energy graph. So notice, the idea is decreasing the reactants didn't change the reaction pathway or the activation energy, but the number of effective collisions did go down, and that's why the rate would indeed decrease if you have fewer reactants. All right, we have a single multiple choice practice problem to try, because why not? It's on this page. We might as well do it. So let's go ahead and take a look. So it says the above reaction will experience a rate increase by the addition of a catalyst, such as platinum. Which of the following best explains why? Well, I'm going to let you figure that out. Go ahead, try it. I dare you. So try it yourself, and when you're ready to check, well, unpause the video. All right, this problem is a little bit sneaky. So in this case, it says the first question says the catalyst causes the value for delta G to become more negative. Hopefully you were able to eliminate that as an answer choice. Boom, dead to us. Because a catalyst doesn't change thermodynamics, and delta G is thermodynamics. Now the next one, it says the catalyst increases the percentage of collisions that occur at the proper orientation. That is totally true for some catalysts. That is, in fact, exactly what an enzyme does. But it's not always true. However, answer choice C, this one is always correct. A catalyst introduces a new reaction mechanism, and that's how it causes the rate to, in fact, increase. Which means, of course, the catalyst does not increase the activation energy, it decreases it. If it increased it, that's actually called an inhibitor. That would slow it down. That's the opposite. So C was the correct answer choice. And guess what? I see that we are now done with this video, and you are now masters of kinetics. I will see you in class for our last fun and exciting day before the test. Yum! Make sure your reaction rate stays high.